Hello everyone, welcome to another video. It's actually our second session on the series of videos I'm going to make on quantum physics. Last time we looked into quantum indeterminacy. We said how it differs from classical physics fundamentally, and we also looked into the schools of thoughts of quantum indeterminacy, and we came up with Born's statistical interpretation and what it means. And now, before we proceed further, I thought that maybe perhaps it is worthwhile looking into the scales and dimensions in which quantum physics best reveals itself. In other words, we're going to have a look at the scales of the micro world. This video is intended for a general audience. There's no fancy mathematics or no technical, details that we are going to mention. It's just to give you an information and an introduction on the sizes and the scales that we will be mainly dealing with when we talk about quantum physics. Now, this doesn't mean that quantum physics doesn't, apply to the macro world. In fact, there are many quantum phenomena that show themselves in the macroscopic world, such as superconductivity, superfluids, etc. But I thought that maybe it's better to just zoom in into matter and see what is matter made out of, and then once we get a feeling of the sizes that are involved in the quantum universe, then we, build upon them. So I thought that maybe as an example, it's better to start with something completely familiar to us, like a drop of water, and want to examine what's inside a drop of water. And want to look into it carefully and see where quantum physics kicks in order to give us a good description of matter, and in this case, let's say water. All right, so we start with this droplet of water. It's a typical drop of water, almost like a perfect sphere, highly reflective. Let's say this is sitting on a plant, a leaf perhaps, and let's say its typical dimension is about 1/4 of an inch. Now, water it has a number of properties, obviously, we all are familiar with. First of all, it is transparent in the optical spectrum. Optical light that our eyes can see, actually can travel through water with a minimum absorption. That's why it appears invisible. It's also tasteless. I mean, there's no, our taste buds are not, activated by drinking water. It doesn't have any smell. It's odorless. And, on top of these, it is called the universal solvent because of its, chemical properties, namely the hydrogen bond. But perhaps it's all of these properties together that makes water such an important substance for living beings. I mean, almost all living beings depend on water. And since water does not discriminate in color and texture and taste and smell, maybe that's why, such a large diversity of creatures can depend on water. I mean, I've never heard of an animal or a plant or a human being, let's say, that hates water. I mean, water, we all drink it and we don't discriminate, or water, let's say, it doesn't discriminate the living beings. So it's vital for all of us, for our survival. So if I look into this droplet of water, I don't see anything interesting really, other than these few properties that I mentioned. But let's assume I use a rather good optical microscope and I zoom into it and I magnify it by 2,000 times. Now, when this happens, this drop of water would become as large as a uh, big room, over 12 meters long. So this 2,000 time magnification really, blows up this, water to this size here. But let's say, well, I'm just looking into a little portion of that. And apart from, let's say, dust particles that may perhaps be on the surface or some minerals or impurities inside the water, if this sample is really taken from, I don't know, a pond or a lake, maybe I would see two different kinds of creatures here, maybe more, maybe less, depending on where I choose the sample. But at this point, maybe the biologist will become interested in looking into what these, uh, organisms or creatures are. So let's say, for instance, these elongated oval-shaped, creatures. If I look into them carefully, they have a, structure like this. They swim around the water. They are called paramecia, and a typical paramecium has this, length. That's the size of it. And as you can see, between 0.05 to 0.32 millimeters, a typical paramecium would vary in size, and they're quite tiny, right? Roughly the same size of these paramecia, a little bit larger than them, are these other creatures here that I've shown two of them, and they are called tardigrades, or in common language it is water. They are named water bears, and as you can see, they're a little bit larger typically than paramecium. As I mentioned, a biologist would be interested in these creatures because they are living organisms. They might want to know, let's say, for instance, what is their DNA, their genetic information, how do they reproduce, what do they consume, how do they survive, how do they swim around, and etc. But from a physicist's perspective, we are really not interested in the details of living organisms. But there's one thing to say, that although all of these creatures are tiny, you see, we're on the micro scale, but nothing weird is going on here. In other words, what I mean by that is that their motions, the physics that governs these scales is actually the familiar classical physics, which the foundations were laid by Sir Isaac Newton in the 17th century. And Newtonian mechanics, or Newtonian physics in general, can actually explain, the interactions of objects that are even down to this size. So there's nothing wrong with Newton's laws being applied to these scales and dimensions. And in fact, you can think that the micro world up to this point is really a miniature macro world. So if I talk about, let's say, velocity, acceleration, force, energy, whatever dynamical variable I have in classical physics, I can actually apply it to the micro world up to this scale. Because once we start magnifying more and looking deeper into matter, then that's where we have to make a transition from classical physics to quantum mechanics. So let's move on to the next slide. Yeah, well, here I still have that little sample of the droplet of water here. And here we start entering the realm of quantum mechanics. Let's say I take another piece, yet a smaller piece of this droplet of water, and I magnify it by another 2,000 times. Now, in this case, the droplet of water is now 24 kilometers in size. Okay, so that's how big we're magnifying things. That's how our microscope is magnifying. And incidentally, this magnification, optical microscopes will be of no use anymore, and we have to use other types of microscopes like electron microscopes. And the reason for that is that we're entering scales in which in order to look into the details and the structures of matter in this scale, we would need light of a wavelength that is tinier than visible light's wavelength. And that's why optical microscopes will be no good. We have to use other techniques. Let's say, for instance, if I want to look into the structure of a crystal, I will have to use X-rays. I cannot use optical light because simply the wavelength of optical light exceeds the spacing between the fine details and the fine structures in the crystal. So, but if I do this anyway, if I magnify another 2,000 times, I would still see some smooth water substance, but here and there, I see some kind of a teaming up, some regions in which there's a little bit more density. I've shown it here schematically by the darker shades of this bluish color. And it's, if I want to make an example, it's like looking at a crowd in a stadium from a very, very far away distance. You cannot tell the individual, people that have attended that, I don't know, whatever it is, a match, a sport game, but you can see that certainly some dynamics is going on. And if I want to zoom in still further, now I can start making, distinction between the different parts of water. And for that, I'll have to zoom another 250 times. Now, at this level, that drop of water is now 1.5 times larger than the continental United States. Or perhaps I can make a comparison like this. It can be assumed to have a diameter roughly about the size of Earth's radius. That's how big I have to, magnify the water in order to see this. And when I'm saying seeing this, I don't mean literally, because as I said, you cannot look into, these fine structures with optical light. So what do I have to do? I'll have to use my imagination. And this picture here is a snapshot of what I would end up with, probably. And as you can see, we see these individual, units of matter, which we call molecules. And in this case, these are water molecules. We all know that they are, shown by the chemical formula H2O. That means each water molecule has a oxygen atom, and attached to the oxygen atoms, they are two smaller hydrogen atoms. And this, you have to consider it as a dynamic, image, meaning that all of these little molecules are jiggling around, they are moving around in water constantly, and they are vibrating, they are turning around, they're making all sorts of motions. At this level, you can still apply Newtonian physics. But if you want to consider the interactions between each molecule or the atoms that those molecules are made out of, then Newtonian physics will start to collapse. So here's where classical physics begins to fail, and I would have to use quantum mechanics. And this is the general Schrödinger equation. We will later look into the details of what these symbols mean. But this would be the equation that I would need to, understand in order to be able to figure out the motions of these water molecules. All right. The universe is governed by the laws of quantum physics. Why is that? Because all of matter that we know is made out of atoms or molecules, okay? But everything is made out of atoms, and down at that scale, the laws of classical physics will not apply. We'll have to replace them by the laws of quantum physics. Now, here's the one of those water molecules that I've magnified, and just to give you an idea how small these objects are, I've written the typical size of a water molecule, not in scientific notation, just to let you know, just to make it uh, look really, really tiny in size. I mean, you should appreciate how small this number is, which is 2.75 angstrom. 1 angstrom is 10 to the minus 10 meters. That is 1 over 1 followed by 10 zeros. 1/10,000,000th of a meter is an angstrom, and a typical water molecule is about 2.75 angstroms in length. At this level, the scientists that are interested in understanding the molecular interactions, they would have to, apply the laws of quantum physics, and this discipline would be molecular physics. All right, but nature is even finer than molecules. It's even smaller than molecules. So let's take this, for instance, oxygen atom and see what's inside it. So let's say if I zoom into the oxygen atom, this is what I would, again, figuratively see. Okay? No one has ever seen an atom. Now, by the way, atom is derived from the Greek word atomos, which means indivisible, right? But nowadays we know that we can even, disintegrate atoms. But if I, for instance, look at, let's say, the oxygen atom in the water molecule, I would find a fuzzy, region here, which is the what we call the electron cloud. But again, I'm saying these are not real images, okay? They are the way that we would like to, explain them to each other, okay? So this is our imagination still, although we know it's true, but no one has ever seen, for instance, an electron cloud. And perhaps one reason for that is that it is a probability cloud, as we discussed in the last video. It's a probability cloud, meaning that there is a certain probability to find electrons in this region. And right at the center of the atom, there's a highly dense piece of matter, compact piece of matter, which we call the nucleus. Here I show it by a positive symbol because we know that nuclei are made out of positive charges. Now, the distance between the nucleus of an atom and the electron cloud is large, is very large relative to the size of the atom itself. What do I mean by that? First, let me give you the scale. So where the electrons, let's say, occupy the space around the nucleus, where they, if we want to say, move around, let's say they occupy typically a spherical, shape here, and the radius of this sphere, the sphere of electron probability, is 100,000 times, 100,000 times larger than the dimensions of the nucleus. So most of the atom is empty space. That means most of matter is empty space, because eventually every thing else is made out of atoms. And if atoms are mostly empty space, that means matter is mostly empty space. In fact, if I want to, give you an example, Imagine I suck out all the empty space out of, let's say, Mount Everest, and then I, try to squish all the nuclei of that make all the atoms of Mount Everest into a compact region. So if I would look into that, it will be probably no larger than a sugar cube in dimension. So that's how much empty space we'll have. Everything is made out of empty space, essentially. Another reason that we think of solid, rigid objects like our, tables, computers, trees, even us human beings, why we feel solid, is just an illusion. We're mostly empty space. Okay, and and by the way, again, because optical light cannot resolve small distances, that's why we cannot see these empty regions. All right, so the radius of the oxygen atom is 0.073 nanometers. A nanometer is 10 to the minus 9 meters, 1/1000th of a meter. And as you can see, and as we expect, the atom must be smaller than the molecule. And in terms of meters, this is how tiny, let's say, the size of an atom is. Physicists that study atoms work in the discipline of atomic physics. Now let's zoom in further. Let's take this nucleus and see what that is made out of. And let's say I'm using the nucleus of oxygen 16. It's the abundant isotope of oxygen. The 16 just tells you that there are 16 nucleons in the oxygen nucleus, 8 of which are protons, which here I showed by the yellow little spheres, and the other 8 are neutrons. Neutrons are neutral electrically, that's why we call them neutrons. Protons, however, have a positive charge. But right now we're not interested in those properties. What makes it interesting, this piece of matter, is that it's one of the most highest density objects in the universe. Right? Putting all of these nucleons together and making a nucleus requires a tremendous amount of energy, which is, we often know it as nuclear energy. The size of the nucleus, the diameter, or let's say here the radius of the nucleus, is extremely tiny and compared with the radius of the atom, as I mentioned earlier, and it is about 3.15 femtometers. A femtometer is 10 to the minus 15 meters. That is a 1 over a 1 followed by 15 zeros. So that's how tiny a typical nucleus is. Scientists that are interested in the interactions in the physics of the strong nuclear force are working in the discipline of nuclear physics. Does nature stop at this point? No. We can even look into a typical proton and find out that a typical proton is still made out of 3 other particles, 2 which are shown here by green and 1 which is shown by blue. The 2 green ones are called up quarks. The blue one is called a down quark. In general, quarks come in 6 different kinds, or 6 flavors. That is literally what we use as a terminology. 2 kinds of these quarks make up protons and neutrons. So a proton is made out of 2 up quarks and 1 down quark. A neutron is made out of 1 up quark and 2 down quarks, which I haven't shown here. The quarks are glued together, really. You cannot find an individual quark in nature, and the let's say force that keeps them together is the nuclear force. Now, perhaps a quark has an internal structure. At this point, we really don't know. but physicists that work in these fields are called particle physicists. And our modern understanding of the universe is based on something that we call the standard model of particle physics. And we have a very, very great and efficient theory, I would say, that works and explains the universe in the subatomic and subnuclear realm. Typically, if you've heard of the CERN Large Hadron Collider in Geneva, the border between France and Switzerland, that is one of the most expensive and largest, let's say, in size laboratories and experiments that we have built. And there are thousands of physicists, engineers that are working constantly there. And in those facilities, they actually, smash these fundamental particles, high energetic particles with speeds very close to the speed of light, and they examine what they are made out of. Now, of course, I can continue this, downsized micro scaling and reach the vacuum energy, the quantum foam, and etc. But just to give you an idea of how small things are when quantum physics really shows itself, it's basically all shown in this slide here. So the type of quantum physics that we're going to study would be applicable to nucleons, atoms, and molecules. So this short video, we will conclude it by showing an image of Dr. Richard Feynman. Incidentally, as a reference, I've used the first volume of Feynman's lectures on physics. It's a very, very good reference book. And apart from that, some of the pictures that I've shown in this presentation were taken from Wikipedia, which is the free online encyclopedia. You can all use those resources. But if you want to take scientific material from Wikipedia, I should warn you that not all of the stuff that is written in Wikipedia, as I mentioned last time, it doesn't go under the peer review scientific process. So you have to be careful when you're taking information out of it because there might be some other misinformation in there. But anyway, Dr. Feynman, he was one of the greatest physicists of all time, and he actually contributed to quantum physics. He even, opened a branch of quantum physics, which is called quantum electrodynamics. And apart from that, he was an excellent science educator. And I always recommend my students to go and grab Feynman's lectures on physics and study them. They're written in very plain language, and they completely cover almost everything that physics has to talk about. We will end this short video by a famous quote from Niels Bohr. He says that a physicist is just an atom's way of looking at itself. Think about this quote and appreciate what it really means. So thank you very much for your attention. Please do not forget to leave your comments, suggestions in the comment section. And I would be thankful if you subscribe to my channel if you like these material that I produce. And if you find this video useful, please don't forget to subscribe. And once again, I would like to always end my videos by mentioning a sentence. If you think about it, our world is a very interesting let's call it an entity. It's an interesting system. We are part of that system. We are not separated from that system. And it is really interesting that we human beings can actually study it, make sense out of it, no matter how weird it turns out. And every time, by the way, nature surprises us. Every time we think that we're making progress and we're finding a good explanation, then nature shows up and tricks us and surprises us with another phenomena. So what I'm trying to say is that the mystery keeps expanding as our knowledge, increases. The unanswered questions are also increasing. So always remain curious, and don't forget that the universe is really meaningless. It is us that give meaning to it. Thank you, everyone, and take care. Until next time, bye-bye.